thought Friday was lightly attended, but we're getting closer to the finals. Um, I do have, if you haven't picked up your exam 2, I do have those ready to hand back. So check with me on your way out. We'll get you that. And I did make some adjustments to the pacing calendar. So I'll go over those quickly. Found out actually we have a little more time than I had anticipated because all the P1s, which I had on separate days, are really part of the assignment for one of the lessons. So 9.1 and P1 are together. There's no I can't find the appendix in the book, so I'll have to track that down somewhere. But what we have is we have the homework that's in WebAssign, so I look over that. And basically for this lesson, they just talk a little bit. The P1 is about continuous variables, so those are in there. When we get to down here, P2 and 9.5, most of the content is in 9.5. Again, we do have some problems to work. So what we're going to do is those, I expanded those days over to 2 days. So like this week, we'll get the content today. That allows us Wednesday. What I'm going to do is I'm going to use that sort of for an early exam review. We'll work through some of the questions from the review that are specifically for P1, which I'm not sure there are, but anyway, we can go over homework. We can do whatever we need to do. So we've got some time there. And then the rest of them will fit in there. Notice we have this Friday here an in-class application. So that's kind of an open day to make sure if 9, 2, 3, or 4 take a little extra time, we've got that room there. The following week, we're actually going to finish everything up a whole week early, leaving the whole last week really as a dead week, as it should be, which we can start reviewing for that exam 3. So we get 3 full days in class to do some review. Again, what I will do is I will look at the review that's been made by the coordinators, because they also make the tests. I will also pull up things from the test bank to help us understand these concepts. And then we've got our final exam. So again, hopefully it's sort of a step up for most people in their scores on exam 2, and we'll hopefully see another step up on exam 3. All right, so we'll get into this, and what we're doing now is 8.5 and 8.6 really were probability, but there's, yes. Of course. I mean, I always look at the review and say the highlighted ones do these. These will cover everything that's on the test. So if you do these as a minimum, you'll have all the concepts. The other ones are good ones to do. Sometimes both of them would be good, but I'll highlight one of them, say at least do this. That will do it. But if you do more, it's always better. Yes. And so, but again, I won't do that. I won't have the access to the final. And then like this last one, there was a couple on the final exam that really, there wasn't anything on the review. So I added a problem or two into the review that address those. So I make sure that when you come, if you've done those things that I said, do at least these 7 or 10 or whatever they are and understand them, you'll see that you won't be surprised. Good question. All right, so let's go ahead and get in. But this has been updated, so you might take a look at that. And again, we do have this full week. And then for finals week, we don't have the finals till Thursday, so there is some slack time in there. And I do have all the homeworks, all the assignments from day 1 of class to open until May 2nd. So anything you need to review on. But again, the exam 3 is only going to be on this new stuff that we've started since section 8.5 and forward. All right. Oops. So we're going to go in 9.1. And as you're going to see today, I'll say most of this content is vocabulary. This is the day where we're really transitioning. They call it random variables, but this is really, it's setting us up. We're going to do some things we did like with rolling dice, but we're doing it in a new construct, which kind of sets it up for statistics. Okay, so we're starting to work more and more towards statistics, thinking either of probability more in terms of relative frequency, how often something happens, right? This idea between probability and relative frequency is a little transparent. They're almost, you could sometimes do the same thing, right? Whatever you roll a dice and how many times you get a 3, that's a relative frequency. But if we do it enough times, then we call that a probability, right? If we only do it 10 times, that's not really probability. It's just that's how many times the 3 showed up when we rolled it 10 times. But we might not see it happening 1/6 of the time unless we did it a lot. So let's go ahead and get into this. Okay, so what is a random variable? This one just kind of, the word itself kind of threw me. I remember studying this and it just took me so long because I thought of it something. Random variable is, as they're saying, it's due to an experiment. So we've actually been using random variables without calling them that. When we rolled a die, it would either come up with a 1, 2, 3, 4, 5, or 6. We assigned, if it got and it was like 2 dots, right? 2 would be 2 dots. We gave it the number 2. If it had 3 dots, we gave it the number 3. That's what a random variable is. So in a sense, we've actually already been using it without calling it that. We just use this technique now where we're making it more formalized. Okay, so the random variable is whatever that outcome is, we assign a number to it. Okay, I could randomly choose one of you or 2 of you from this class, and then your name, I would choose you. That's sort of just regular probability. What's the chance of it being a man or a woman? We might do that. But if I were doing with random variables, I would choose you, and I might assign the random variable to be your student ID number. Or I might assign your age as a random variable. So we could do a lot of different things, but we would assign a number with the event of choosing a particular student. There would be a number assigned to each student. So this is where it makes whatever we're doing, instead of using like a name or something, it makes it numerical. And if we have a number, then we can use all the formulas for statistics. Statistics is all based on number. So this random variable thing is a way of assigning a number to an event. The event might be you got coffee or you didn't get coffee. And so you might assign a 1 to when you got coffee and a 0 when you didn't. So you see how that can work. So it makes everything numerical. That's all that's going on here. So something like here, you select a lawyer and use his annual income as his, because maybe you think the richer lawyers must be more successful, right? So maybe you're looking for that. The salary could be his or her random variable rather than the name. So each outcome, whatever it is, we're randomly doing something, pulling it out, we're going to give it a number. Okay. And again, in some senses, we've already done that. Now, like with playing cards, we didn't do that. We didn't do it much in this class, but a lot of times they're doing playing cards and they, King of Hearts or something, but using random variables, we'd have to assign a number to that. Marbles in a bag. Remember, there was red marbles, green marbles. What we'll see, there's an example in here a little bit later, we'll actually assign numbers to particular events. So if we got 3, we're drawing 4 marbles and we drew 3 red marbles, we might assign that as 3. We only drew 2 red marbles, that would be 2, the number 2. Okay, so we're going to set up our events in a way that we can assign a number to it, and then we can do statistics. So this is the sort of the opening the door to statistics for us. So first of all, part of what you're going to do is there's different types of random variables, and their types are dependent upon what kind of numbers get assigned. So we're going to assign a value. Now, if I assign your student number to you, and we randomly choose you, and you've got your student number, do your student numbers have any decimals to them? they're a particular number, and so and each of you will have a different student number. That's the way it's set up. We could use social security numbers. Same thing. Each person is supposed to have one number. That's what's called something like that would. I guess I'm getting a little bit ahead of myself. Um, well, okay, let's back up a little bit. So we've got our sample space of what we're choosing, what is randomly being chosen. This is very abstract, but there are 1, 2, 3, 4, 5 different events in this sample space. I don't know what they are, but randomly one of these 5 events is going to happen. If this event here is chosen, then we assign it 0. If this event here is chosen, we assign it 5, -1, 2, and 0. So we 2 different events could actually have the same number. So, and again, we have no idea what this is, but what we do is that would be the random variable. So again, we've done this before, rolling a dice. We assign it the random variable, how many dots are facing up. 6 are facing up, it gets assigned to 6. Okay. Could you have x equal to 0 in this case? With rolling a dice, could x ever be 0? No, because you can't roll a 0 unless you have a special dice. Could it ever be 7? No. Could it ever be 2.5? No. Okay, so there's a lot of things it can't be. It can be 1, 2, 3, 4, 5, or 6, but it can't be anything else because that's what we've set it up. Okay, I'll get the vocabulary's next slide. You could be choosing mutual funds, and maybe you set up that the random variable is the number of companies in the fund portfolio. So mutual funds buy stocks of companies, and so if they had 10 stocks, they would be x equals 10. Okay, and this is a way you could do sort of statistics by how many stocks a company, particular mutual fund has in its portfolio. Okay, so again, multiple ways to do this, but you always have to have that definition. What is that variable recording? Okay.
So there are several types of random variables. Actually, 3 of them that we'll be taking a look at. So there are discrete and continuous random variables, 2 main types, but within the discrete, we're going to use 2 types. So a discrete random variable in general has only specific isolated numerical values, such as the roll of a die. So the numbers for that would be 1, 2, 3, 4, 5, 6. And then also dollars in a randomly chosen bank account. Again, dollars still have decimals, so $100.23, but you can't have 23.5 cents, right? You can't have less than that. So these are also discrete, which means that the data ends up becoming points, not lines. So you could actually, on a graph, you would see space between your data. Now, the discrete have 2 types. The discrete would be infinite, such as the money in a bank account, because there's no limit on how many dollars you could have. I mean, actually there is. There's nobody who has an infinite number of dollars, but we don't have something set as the top limit. The finite random variables would be like the roll of a die, because there's limited 1, 2, 3, 4, 5, and 6, and that's all you can do. There's no unlimited. And the dollars, it would be $1, $2, $3.23, and so forth, and actually a lot in between here, but we get a dot dot dot, right? There's no end to it. There is one other type of variable we'll just deal with a little bit, and actually in the homework you'll just have to identify what type of variable each one is. And the last type is a continuous random variable, and that means something that would graph as a smooth curve. Things that are measurements, such as temperature in Central Park. So we could get 23.4 degrees, 23.45 degrees, and so forth. And same thing with measurement of, say, the height of an athlete, anything. Anytime we're measuring, we get a smooth, continuous data. All right. So here's some examples. If we have the random variable of selecting a mutual fund where X is the number of companies in the fund portfolio, what type of data is that? Well, you can only have set numbers 1, 2, 3, 4, 5 companies. You can't have 1.5 companies. You either have a company or you don't, as far as what's in the portfolio. However, there's really no upper limit. It's not like you're limited to only 100 companies or even 1,000. Although most mutual funds will, they won't have an infinite number of companies, but we have to leave it open-ended because there is no natural limiting value. So it is a discrete and infinite type of random variable. Second one is you take 5 shots at the goal where X is the number of times you score. And again, what does that data look like? Well, you'll either get, you're like me, maybe you'll get 0. You'll get 0 goals, or you'll get 1, 2, 3, 4, or you'll get 5, but you can't get 6 goals because you've only shot 5 times. So that is finite. It's discrete and finite, but we just use the term finite here. And actually, for the discrete infinite, you'll see that just listed as discrete. And the last time, the measure of an object in centimeters, just as we discussed, it really is any positive real number. Can't be negative, but that's okay. But again, no limit on the upper end, so it is continuous. And if you wanted to talk about it, it would be infinite because there's no upper limit. Okay. So finite random variables will let X be the number of heads that come up when a coin is tossed 3 times. So the question is we want to be able to list the value of X for each possible outcome. What are the possible values of X? And so we start with what is the rule? The rule is that X is a rule that assigns to each outcome the number of heads that come up. So what does an outcome look like? Well, here we go. You can get 3 heads. You can get 2 heads and a tails. You can get a heads, tails, heads. So here are all the physical outcomes, and the value of the random variable that we assign, rather than counting outcomes in this case, we give it a variable. And so if you got 3 heads, your value of X is 3. 2 heads occurring here and here, and then only 1 heads, tails, 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 heads, tails. There's 3 times that happens. And if you got all tails, then there's 0 heads. So these are the values of X, and these are the outcomes. Now, in the earlier section of probability, we really stopped. We just sort of looked at what the outcomes were, and then we counted them. And we might mention it, but we didn't mention a random variable. We would just say how many different ways to get 2 heads. And in this case, we're actually assigning it to a variable of X, that X equals 2 in these 3 instances. And so if it was, what's the probability of getting a 2? The way they ask it now is, what's the probability that X equals 2? And we would just count, well, there are 1, 2, 3 ways of getting a 2. There are 8 total possibilities, and so this is how the probability problem now looks. Whereas before we might say the probability of getting 2 heads, and we would have done the same thing. We would have counted the outcomes here, here, and here, and said that there were 3 8s. So you see, very similar. It's just we're kind of focusing. We've got one level of abstraction going on. So the possible values of X are 0, 1, 2, and 3. So those are the possible values, and then we can come up with their probability distribution. And what that is it's a listing of all the probabilities for each of the variables, right? So we give each random variable X is associated with the event, and then we find what those events are. So when X is 0, that happened only when we got 3 tails. When X is 1, there are 3 different ways that could happen. Event 2 is X equals 2. There's 3 different ways. So notice we're looking at the random variable sort of first. It's a different way of doing it, but we're still counting in the similar way. And so in this case, we have the probability X is equal to 0 would be 1 out of 8. Actually, let me go with this, get my title. The probability that X is equal to 1 would be 3 out of 8. Probability that x is equal to 2 would also be 3 out of 8. And then the probability that x equals 3 is 1 out of 8. If you wanted to, the probability that x equals 4 would be a 0 out of 8 because it really doesn't exist, right? You can't get 4 heads if you've only rolled 3 times. What you'll see is this always will add to 1 because that's 100%. That's what makes it a probability. If it adds to more than 100, then it's not a probability distribution. If it adds to less than 100, it's not a probability distribution. But in this case, it is a probability distribution. So what is a probability distribution? It's the collection of all the probabilities of x. So we list each x value and what their probabilities are, and that's a probability distribution. And typically you'll see it in a table like this. Big X is what we use for random variables in probability experiments, and then little x is the actual outcome. So x equals 0, 1, 2, 3, or 4. Well, in this case not 4, but 0, 1, 2, and 3. And we have all our probabilities, and again notice the total, the sum, is always equal to 1. 8 out of 8, 8 eighths, which is 1. Okay, that will always happen. So when we have a probability distribution, we can also look at not necessarily what is x equal to, but sometimes we look what's the probability of x being greater than or equal to 2. Well, it's 3/8 that it's 2, it's 1/8 that it's 3. Those are the two options. We add them together, and so it would be a half. A probability of x being greater or equal to 2 is 1/2. Again, just a level of abstraction of the way the question is asked. Instead of asking what's the probability of getting 2 and more heads, we just assign it x is greater than or equal to 2. We can also use bar graphs, and in the homework you'll see that that is one of the things you'll be working on. They'll give you a bar graph to create. You'll need to sort of click your mouse there and drag it up to where it needs to be. So figuring it out, but we can make histograms of probability distributions, and again the total area, if we were to calculate the area of each of these rectangles, kind of like what we did in calculus, right? The area under the curve will always be 1. All right. Here's another example that we started with, the probability distribution of this particular thing, this event. Whatever this and this are, they both get assigned the random variable of 0. There's some abstract event over here that gets assigned 5. Whatever event this is gets a -1, this gets a 2. So our events are -1, 0, 2, and 5. And assuming equally likely events for all of this event space, we just sort of count how many. So there are 2 zeros, so that's 2 out of 5 things happening. Equally likely is the assumption. Again, that's an assumption that is being made. Not everything is equally likely, so we've got to check on that. But if they tell us it's equally likely, then we can get our probabilities. 1/5 for -1, 0 gets 2/5, and 2 is 1/5, and 5 is 1/5. So probability distribution here. Again, they all will add to 1. We end up with 5/5 if we take the sum. Okay. Here's our probability distribution when rolling a die. X is either 1, 2, 3, 4, or 5, 6. And again, each has a 1/6 probability. If we were going to look at rolling 2 dice, we would list numbers from 1 to 12, right? And not 1 to 12, we'd list 2 to 12 for 2 die. 2 dice. I guess that's the plural. Dice is plural, die is individual. And we'd have their associated probabilities. 2, the probability is only one way to roll a 2, 1 out of 36. And 12 is you roll 2 6, so that's 1 out of 36. And each of these other ones would be something in between. So we could set up that table as well, but I think mostly we'll be dealing more simplistically with just 1 at this time. Okay, so that's a probability distribution. And again, with probability distributions, we can ask questions more abstractly. So the question we might look at is what the probability that x is less than 3, and we come back here. Less than 3 means either a 2 or a 1 or a 2, so that's 1/6 plus 1/6, which is 2/3, or 1/3, sorry. 1/6 plus 1/6 equals 2/6, which is 1/3. Probability that x is greater than 1 but less than 5, well, that means x is a 2, 3, or 4. So we add those together. That is 1/6 plus 1/6 plus 1/6. And when you add that, you get 3/6, which is 1/2. So again, nothing incredibly new, just a different way of asking the questions using random variables. And finally, one of the homework questions, I did do a screen capture on this, is to actually set up the frequency table. And so some of you this might not be too big of a challenge, but I just wanted to go through. So they will give you these what they call the brackets. Let's see, what did we call it? Bins. I think we call it data bins. So we set up a table, and our data is between 2.1 and 4.0. What we're going to do is we're going to count how often that occurs. Okay, and oftentimes we could set up a place for a tally, and then number, or you could jump right to the numbers. So between 2.1 and 4. So let's see, we just go along the date. 3.8, that's one of them. That is between these two numbers. So I'm just going to cross that out, and then I just keep looking. Oh, there's only one. So there's one of those numbers. And then they want 4.1 to 6.0. So that would include the endpoints. So 4.1 would be here. And again, the 4.3 is one of those. And again, I look to see anything. This goes 6.5 is too big. That's it. So that's only one there. And then we could do 6.1 to 8.0. And again, we're looking for values between these two in the data. And 8.0, that's at the endpoint, so we'll count that. That's 1. 7.4 is there, so we'll count that. 6.5, we'll count that. 7, 8, that, and that. 8, we'll count that one. We won't count 8.5, that's too big. 7.5, we'll count that. 7.0, we'll count that. Count that one. And 7.5 gets counted. 8.1 is too big, so we don't. So there's 10 of those numbers. And then lastly, the rest, 8.1 to 10.0. We could just kind of count what's left. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of those. Okay, so that's the frequency table. Oftentimes we want to turn this into a relative frequency. So the number here is just the frequency. Relative frequency is writing it as a percentage. So this is 10, 8, 9, 8, 9, 10. So that's 20. There's a total of 20. So this has a relative frequency of 1/20th. This is 1/20th. This is 10/20ths, which is equal to 1/2. This is 8/20ths, which is equal to 3/5. Okay, and so if we added all of these together, we would end up with 1. That's what's got to be the case. And change it all to in terms of 20ths, and if you left it as 20ths, you've got 10, 18, 19, 20. You get 20 20ths, which is equal to 1. So that's a probability distribution there. And then they'll ask you some questions about it. But that's the end of the lecture. So take a look at the homework. Wednesday we will be having as a work day to go over the homework, because that included both 9.1 and P.1 in the appendix, which is looking at the continuous random variable. And we will move forward with that. So 13 or 14 questions to work on. Thank you.